Hello, everyone. Let me welcome you to this webinar of PLC2. Today, we'll be talking about the target reference designs and mainly about the adaptive SoCs. We'll be explaining where that actually comes from, where the notion comes from to use these elements. And I thought to go over basics of the adaptive SoCs first, then explain why and where these target reference designs are available and how they are actually converging or even over the different families. We'll have to talk about this idea of how to increase the performance or increase the design level of these target reference designs to the actual application that you may want to use in your own designs, and then finally get an idea of what the effort is to put this whole setup then together and really have a complete design. If we're talking about this idea of building target reference designs, of course, this mainly makes sense for a bit larger and complexer devices, not just the pure standard FPGAs. So we're talking about a product line of adaptive SoCs. When you have been maybe looking into such adaptive SoCs before, the most prominent ones right now in the market are the Zynq Ultrascale plus MPSoC. What you see in here is really a split between the native processing system on the top and the fabric that still can hold a pure FPGA design, as you may know it from other FPGAs. So it's the best possible combination in a way with hard IP that always behaves in the same way and always delivers the same elements to your designs, plus the very flexible part of the programmable logic. When you look into these elements, you see that there's different groups of processors. Of course, there's the APUs for application level software running. There's the real-time processing units that are really there to do more like low latency accesses, or at least defined latency accesses into the hardware. And many supporting elements that are related to, say, like building a complete system on a chip, as it's called, SoC, already with IP and many IOs that are already attributed to this PS part processing system in this case, of course. And we're having lots of additional support. And one main interesting thing is that you see that there's, of course, on-chip memory, but also the DDR external interface is governed by the PS system. So in the PL part, you would typically see all the things and elements that you know of the Xilinx as of old FPGAs. You have the IO groups, and you have the block RAMs, ultra RAMs, distributed RAMs within the actual fabric, and the DSP blocks that go with the actual logic level that you want to see. Just as a summary again, one distinct thing within the Zynq Ultrascale is that you have the A53 processors, up to 4 of those working as a cluster. So you can easily have a symmetric multiprocessing Linux system with this. And basically also you have the R5 processors, not only 1, but 2 of those. The main difference of these elements are really, what do you want to deal with from a software perspective? Do you really want to have a low latency access into the system, or do you want to have a completely coherent processing level for your applications? This complete setup is actually complemented with a platform and power management unit, so that you in your designs don't necessarily have to run all of these different elements. If you don't need them, you can basically do power management within your life cycle of your application. And that would basically help you to save power when you're not in need of the performance. And the fabric, as we said before, there comes the IO, very typical for Xilinx devices, the transceivers on the high-speed side. These would come in with up to PCI Express Gen 4, or you can build up 100G Ethernet interfaces on that fabric side. Of course, the PS part, the CPU fixed IP part, is not capable of doing these high performance level things. So this is where you have to actually integrate both elements into your complete design. A very big important thing for these families is, of course, to figure out a scheme how you want to configure your system and how you want to manage it with respect to secure applications or whatever kind of effects from the outside world. So basically, we have the processors on the PS system. We have the fabric to actually do your very specific high-performing logic design, and you have the infrastructure to keep this whole thing together. When you look for the Zynq Ultrascales, you will see that there's quite different products in the market, and they scale with respect to IP that is available in only the higher level of the devices. So when you look into video processing, when you look into data processing of a certain kind, you would rather go into the larger devices like the EV series, because this guy has internally already an IP that can yield the video coding for some certain applications. So if you're doing like HDMI to display port or the other way around, or you do kind of whatever kind of encoding in your system, you will basically have this unit at your hand. So 3 core family contributions, and that basically makes up the Zynq Ultrascale. Now, if you have these processors of the various kinds and you have this logic level that you need to program, it means in the end that you have to go through the design processes for each of these things. And maybe if you're starting to introduce a technology in the engineering community, this may not be completely straightforward, because it's actually utilizing many different heads of designers, basically batches of designers that work on these elements. So one of the good things that I said is really that the architecture of these elements are all the same. So the way that these devices are starting up, for example, out of reset is always the same. And you can get control in a very similar way of all of these designs. The important thing to know, I didn't mention that before, is that the hard IP, the PS part, is the one thing that governs the wake up of the device. So you will have to provide your very first non-volatile memory, your very first design contribution to that part of the device for it to access and to configure the complete downstream. So that's the concept of these devices. When we're talking about the Zynq Ultrascale Plus MPSoC, that's not the only device that we have in the portfolio of the adaptive SoCs. There's also the Versal family around now that is really a much higher scale, scale kind of version of what we have seen before. And it's basically the fastest thing that you can get in this context right now. You still have this group of processors. These group of processors still consist out of the APUs, which is the application level thing that is more into the cache coherency approach, and the RPUs that are really there for giving you the low latency kind of accesses into the system. But what has been split off from this PS part in the Versal design is really the DDR interfaces, because they are now not bound to the PS part, but they are governed, or they are made available throughout the device with the network on a chip. That has certain advantages, of course, because you don't need to multiplex data on these interfaces. You can separate them out. So if you use multiple DDR controllers, they would all be bound with the lowest latency path to your particular logic implementation, and you can have another DDR interface that's bound for your processor and only take care of like the least traffic between those. Now, when you have such large designs, or even heterogeneous designs with the different groups of design elements that you need to do, you need to put software into the CPUs. You need to basically do the digital design in a classic way on the programmable logic. And for other devices on the Versal side, there's even yet another complete IP that needs a different design approach. That's the AI engines, which is basically a vector engine array where each vector engine needs to get its kind of operational code, and you need to take care about the data movement between these. So there's quite a lot of differently scaled projects involved, and the tool chains are helping you to do that. So you can be like approaching it from each and every of these domains, but the distinct thing is you have to provide the content for all of these different domains always in your designs. This is where actually this idea of the target reference designs come handy, Because from my perspective, and I'm working that way typically, is that if I have something that I want to focus on, a design solution for a particular problem for a customer, I don't want to spend a lot of time to set up the rest of the device. And I'm trying to look at something that's there and readily there for me to operate on. So in comes the target reference designs. And the idea of these is really that it's ready-made, complete stacks of content or design elements for these devices that you can easily plug and play with your own particular solutions in that way. So I have been putting together this idea of the different families we have. Basically, I added beyond what I said before, I also added the Kria SoCs now, because from a technology perspective, it's really a Zynq Ultrascale device, but it's kind of from a design perspective, how you approach it, how you deal with it, slightly different than the tool chains. But in the end, it's the same topology. So you have this compute part, you have the FPGA part, and you may have additional features like the AI engines in the Versal. So when we are going through these things, you see that there's different point repositories or levels how you can address or access these. One important thing to mention is that AMD is trying to push these reference designs on a per release basis. You will see immediately in a second that it's not always happening exactly that way, but basically say like there's a continuum of designs that are moving forward with the releases. Why is it called targeted reference designs? Well, the idea basically is it's bound to a particular device or a particular development kit. So when you look into the portfolio of AMD, there is Zynq Ultrascale development kits, there's Versal development kits, and there's, of course, the Kria stuff all around. And depending on what you actually have in your drawer, and this is where I come in, like a hunter and gatherer. Basically, in this case, I have everything here. That's the nice part. But no matter what you have, you can focus in on these designs, and we will show, I hope to show the equivalency in a sense from a design approach. Of course, there's different target reference designs because the designs are focusing on these devices and they have different connectivity, but also the different topics would actually mean to have a larger device if you want to put it overall and it's just not available. So you have to kind of splice it in some way so that there are some designs around that are taken into the multimedia stuff more, some specific for the robotics side of things, and then to demonstrate certain features of the devices. But what's there for all of the families, and that's the important thing that I came up, or why I came up with this presentation today, it's that the base TRD is available everywhere. And that's mainly there to kind of cover the basic connectivity and trying to make use of a higher level Linux flow so that you can really have a complete full stack design out of these base TRDs. Something specific for the MPSoC is that these are always these devices with the VCU. That's the video unit that I was mentioning before that can do the H.294, 95 kind of conversions, and that's why they are there. Yeah, just to give you an idea before I dive into the availability and how you can find these things. That's just a prototypical TRD now in this case, and it's exactly this VCU TRD of the, in this case, ZCU 106. I will talk about that in a moment as well. The idea behind it is really that you have this kind of input cluster of things, and all the resources that you have on your board would basically be mapped there. So you may have like I2S or SDI type inputs. You can have directly camera attachment on your board, and you can have any kind of network-based or other higher speed connectivities there. So there's typically some kind of capture modules that are already covered. And if you want to play with maybe like video input and you have a USB camera or you have a MIPI camera, so you can basically switch your design easily between the two without having to think about the interfaces and the designs in between. maybe one thing said about these kind of video processing units, at times there are IPs that require special licenses for these kind of data paths. But if you want to bother about these, there's also other solutions around for sure. The typical approach is that you go into DDR memory from these input cluster. And of course, this is where something like a video buffer can be allocated, but it's not like statically allocated in the design. It's something that you can do on a per processing basis. And from there, you can do a memory to memory operation on image processing, for example. That's now, of course, the fancy designs that you want to see typically. And this is why this is the very prominent feature in there. You can have anything from AI accelerators to just standard DSP algorithms, whatever, out of the box. Or, put it like this, you have to basically do some of these overlays in your specific fashion yourself if you want to do specific customer operations, but you can simply just use it as a pipeline, of course. And you have your output pipeline that basically then also can scale into, if you have video output, you can go directly to a monitor, or you can go into specific technologies for the particular domain that you're working in. I think the SDI part is also somehow covered with some licenses, but that's a side note. So I'm showing this right now, and we'll be going to the next one as well. The interesting moment here is that the structure of these TRDs is always set the same way, trying to cover all the inputs on the boards, trying to basically deliver through a pipeline to the output cluster of the boards, so that it's basically built in a way that you can use all of these inputs and outputs out of the box almost, and then you are depriving yourself of the effort to have to go through this implementation of all of these interfaces. And of course, the dev kits with the fixed layout and PCB stuff and the connectors that you have will yield finally that time enclosure and all of these kind of things on the I/O interfaces are already set up from the basic designs. So what does it mean? Basically, when we go into the web level of things, that's always what I tend to do. So you go into, for a particular device that you want to look at or a particular dev kit you want to look at, you simply just use Google to get into the AMD side. So AMD VCK190, that's a Versal board, the Versal board with AI engines and everything on that. So that's kind of the high flyer solution, and just using TRD. And it would basically give you a list of different combination of documentation versus the actual GitHub repositories versus some hints and scribbles and community discussions in that case. What we want to go for first is to really look into, say, like the central storage for this particular board, and that's within the Xilinx Y-key. When you look into it, you will see a list of boards or reference designs here, 3 of those basically, and a version for which version you can find it. I was claiming before that AMD is trying to push it forward with each of the releases. Now you see that particularly this board is kind of a bit lagging. That's most likely because there's also the next level of Versal going, and this is kind of the very first version of the AI engine devices. So when you look into the other boards, you may see different results, and I will show you in a second that this is simply just the way it goes. So from here, I would be able to go into the particular specific sites. Here you see that this is already a GitHub link. That would mean in this case, I can download the complete required data set for this reference design out of the GitHub repository. We can do that, just have a short look. And then you see, we'll be talking about these different steps, which means every directory here really relates to a design step in a second. But here I could basically check out from GitHub, as you know. And the sad part in a way is that it hasn't progressed for the last 3 versions. We'll see the newer versions of Versal also have the AI engine in different physical representations. So the IP has been progressing, and these guys are then more prominent. So, but that's common, I guess. In the end, what's important is that in the end you have a quite extensive full documentation of these TRDs. Some are published in the GitHub IO level, and some are actually published inside the AMD documentation portal. So it's important to know and understand that kind of everything is focusing towards the documentation portal these days, but the actual TRD and very special solutions may still be there to progress. I cannot really tell for sure that these would be like the latest revisions always, but this is why you have the revision histories, right? So that's the way that it basically goes. And the technical documentation as referenced here is of course something that you would find as a user guide 1442 also if you have the AMD tools installed with the doc navigator as true PDF. So that's absolutely okay. So that's it. Yeah, let's maybe just look into the sequence of things because when you get this kind of repository, it's actually pretty large. I will show some of the details later, but basically what it brings inside is really different representations based on different assumed camera setups that you can have. For example, here you see a single camera module, but here you can see even a quad camera module. So if you try to do some kind of vision collection for some AI that moves through world, whatever, you may need more cameras than one. And that's basically a very good vehicle. But of course, these reference designs are not bound that you would have to have these kind of cameras because some of them are quite expensive. But you can have any kind of sub-design that scales differently. I'll show that in a second. The important thing is that's what you already see in here, a solution that would only go from HDMI in to HDMI out, for example, so that you would only do the processing with your stuff. And that's kind of the same approach between all of these boards. Now, when we were looking at this list, it has Peta Linux and platforms with it, and it has overlays. So we'll be dealing with in the next few slides with the idea of the platform as a hardware platform, but when you look into current AMD tools, the complete set of say like closed or distributable blocks of things that you're doing would always be extending it to the next level platform. So basically, I'm doing a hardware platform, I'm handing it over to the software, it's called the software platform. I'm working to package it together with software, it's yet again another platform. So I can basically claim this, this platform name, but the important thing here is that it will be a classical starting point from Vivado. Versal specifically cannot be built completely in Vivado if you're using AI engines, so you need to have some support from the Vitis toolchain, but that's a different level of things. But if you have a platform that basically, for example, governs these IOs, as we have seen before, so the platform would basically try to cover all of these IOs, for example. And then I can use the data path in between to process my stuff as so-called overlays. So I can basically build this platform and then put on top additional content based on my application. And for as an example, there's two overlays already mentioned in the design. One is really a DSP classical element, and one is a XV DPU. Who may have heard of Vitis AI may know that this DPU is the deep learning processing unit, and that would be very much lending itself to image processing. So not that we only have the Versal adaptive SoCs, as I said, like it's converging for the other guys. So you can look into the Zynq Ultrascale TRDs as well. There's also many different flavors of it around. The very typical thing is, in this case, the VCU TRD, because the development kits that are mainly in focus, which is the ZCU 104 and the ZCU 106, are the ones that are basically very much prone to these things. So you see also in this case, we have a propagation to the latest version. And this almost latest version, well, basically you could say now it would be 24.2 already since last week, but we don't have it there. If you go to this latest version, I could just put it in here. You may find something like this. It's still under construction. So for this latest version, right now, the repositories cannot be downloaded from here. It's simply just not ready for the mainstream, I guess. But when you go back to earlier versions, so I was just jumping on 2022.2 today, then you will be able to figure out somewhere it will tell you how to download that complete thing, and you will basically be guided into your Xilinx account, most likely in this, no, that's the tool download, but there's another download for the design. And then you will be able to already have these designs in place. If you don't want to use these designs and build the complete thing, you would be able to just download the SD card images also from that context. So that's basically the idea of it. Okay, and also for the VCU TRD, you will find a user's guide as well. So that's pretty important to figure out that there are different layers of information and you have to bring them together. And that's basically the story. We'll be visiting Kriya later, but I'm just trying to get back into the moment. So talking about this idea of the TRD, even when it's specific for one board, and the board has multiple connectivity and you don't want to bother about all of these IPs building it yourself, you can always start with the TRD, but you can also scale your designs with respect to different boards. Because when I'm just flipping over to the ZZU104, which is a smaller kind of, slightly smaller Zynq Ultrascale board, just remember what we've seen before. It's a lot connectivity on the input side. And on this board, it's just a bit less. So, of course, these TRDs scale with the givens of the boards, surely. But in the end, you can see the same structure as it has been before. So you have the input pipeline, you have the output pipeline, and you have your processing from memory to memory. So that's the generic concept. That's not saying that if you're in your final design, you would want to do exactly the same. You may want to do some kind of direct streaming from your input path to your processing, of course. But as a tech demonstrator and some kind of evaluation of a particular module within some input that you create and some output that you have to push, it is quite convenient to operate in that way. And we'll see that in a moment. So basically, that's the kind of idea. Just keep in mind, even if I would place the Versal block diagram here, the Versal board, the VCK190, it would just look pretty much the same. So that's why you will see in the end, then in these descriptions, always these kind of connections of these boards. So you will have basically your HDMI level connectivity, you will have your local camera connectors, but you will always have your USB and other things that you can basically use in there. So that TRD level, depending on the way you build it, would be requiring some of these elements, but you can always find a way not to use these so that you're basically free to do whatever you need to do. The important thing for it basically is that it's pretty fast because it's kind of, you don't have to engineer all of these different bits and pieces, and it's basically straightforward to build. Well, put it like this, each of these reference designs has slightly different way of, say, like operating the make files, but it's kind of converging. So it has been around for, say, like since 2020 or something like that. So you see that there's some synergy to actually get these things working together in some way. Okay, so why is the TRD set up in that way? So that I said, like, I have this input cluster, the output cluster, and some processing in between that actually goes along with this idea of the extensible platform and external interfaces. So earlier, very classical Zynq designs, PS part plus FPGA part, you would build the complete setup and the configuration of PS and PL inside Vivado. So that would mean in the end, you get some bit stream and some configuration files for your devices. That's then handed into some software development tooling. And in this case would be like the traditional embedded flow. You're fixed, you're building your address map and your IPs that you are using. you're configuring that stuff, and you would basically hand in the address map into the software development, plus the information, of course, what certain parts of this address map should do. So that's a very traditional flow for embedded designers. Microcontrollers that you can buy will not be able to be extended. And in this case, of course, it's quite common. And for the Zynq Ultrascales and even for the Zynq 7000s, and that's quite common. As I said before, some parts of the Versal for some subfamilies will not be able to follow that path completely because you need to control additional tool chains. Like I said, these vector processors on the AI engine, you will not be able to do from Vivado, right? So basically, there is a concept that is called the extensible platform, where Vivado is doing as much as it can or as much as you want to have it doing. Typically, you would go for the interfaces. Typically, you would go for the interconnects between PS and PL and define that. But then within the PL part and within these new IPs, you kind of freeze this design in a half-baked way. Well, it still is a complete bitstream. It still is a complete design. So it's really functional, no problem there. But it's at least marked for extension. And this mark for extension then basically gets picked up by Vitis, and you have a software-defined flow. That software-defined flow would then be able to integrate additional hardware blocks by means that we will see in a second. So you can basically extend whatever the original platform was, and thus extensible platform. And that's in these TRDs, they are built exactly that way, right? So the elements that you build out of the box, when you check out such a repository, you will see these steps. I was mentioning it before with respect to this repository layout, that you have platforms and overlays. And the typical thing is platform is what you will be seeing completely carried out within Vivado. And the overlay stuff, the project level, is governed by Vitis toolflow. So this is where we come from. And even to educate yourself with these flows, because it's not that common in the community, I would guess yet, then also to look into the build sequence of these TRDs is very instructive, basically. So what does it mean in the end to build something like that? It's really, you are starting off with the classical idea of what do you need from your IO level, what do you need from your fabric, what should be done in the logic, what should be done in the PS part. So the sequencing of, or the partitioning of the design is very mandatory and important with these approaches. And it basically means that you're picking up the platforms from hardware and build them into something that Vitis can digest as a as an extensible platform. So you would basically know in the end what ports, for example, of some XI interconnect are already used and what are still not used, and how basically it can be upscaled to use these XI ports for some internal interconnects. So that's the idea of this interconnection approach that Vitis takes to extend such an embedded acceleration platform, and that's really what we have in place. So basically, you have the base platform, you have the CPUs that can run any kind of application, and you are talking about extensions that would be kernels in this case. And these kernels are basically controlled by the CPU. So typically, where you come from, you would be calling a C function on the CPU, but you think to carry it actually physically out in the hardware. That's one way to think about this kind of acceleration approach. To get this properly done, there's a management layer and some agreed functionality in these kernels that's called Xilinx runtime. It's basically orchestrating these kernels in a sense of start, stop, and status query and these elements, and some address pointering updates or whatever. So it's not a big layer of things that are happening, but the number of kernels, if they're growing, then it can be interesting. So that's something different story to learn in this case, but just to make sure that we get this idea of the extensible platforms. So the embedded acceleration platform is an extensible platform, whereas your traditional embedded design work would still be able to carry it out in this case. So this acceleration platform actually makes use of the device split between the PL part and the host part, the CPU, in a way that there's a defined interface how you deal with it. Before, you may have looked into some IPs in your PS, in your PL that would basically have an address map, and you are governing with your driver what the whole thing should be doing. In this case, in this complete accelerated tool flow, it's meant to have like all devices or all kernels having the same structure. So what we see, we have the platform level that brings some IP that's already fixed in there. You have the IOs. It's better to do these kind of things, of course, in the Vivado design, because that's not easily extended into the software-defined concepts. And you have a host code that would be able to talk to this PL part in a defined way. And that basically is used by your application. And then you can put any kind of additional logic as long as it fits into your device fabric. And that's what we basically want to emphasize here. So yeah, let me maybe just go back into the real world in this case and show you what this really means. So I have been at some point earlier, well, way back, built one of the Versal designs, the TRD that we were looking at, the VCK190. And basically this guy has a hardware built underneath it. That's what we said. So the actual platform, the extensible base platform that you're building, you're completely building from within Vivado. So when you are checking out this repository, when you run the make files for the actual platform thing, you will get a Vivado project underneath it that I just opened and tried to show you in a sense. So this is kind of specific for Versal, of course, because the AI engines are not available in the other devices, and the NOC is not available in the other devices. But what you see here already is I had been like, the design is incorporating all of the DDR controllers in the device, and it's incorporating the AI engine, at least addressable from a control port perspective. There's no functional ports in there. The functional ports are these things that cannot easily be described on the physical layer of Vivado at this point. So what we still have on top, let me just get this back into perspective, is we have additional cores, and we were talking about, for example, MIPI interfaces for some of the IOs. So inside there, you'll find a proper MIPI pipeline with IPs readily used out of the library, of course. And you have an audio pipe as well. So I have chosen at build time this small representation of things. You can use this quad camera thing there, and then it's going to be a bit larger in the end, right? So that's the kind of setup we have. Yeah, the display pipe, of course, is also showing, and there you see also some HLS-based kernels. In this case, that's the video suite that are represented as HLS kernels, and that's basically what you can see with any kind of HDMI-based transceivers. So you will see also these connections there, and that's our setup as we have it out of its nature. So that's really the starting point of building. And then, as we said before, with this setup of the repository, we have the platforms to build, and you will have the top level makefile is governing all of your targets. So you can do a complete SD card build, which means it goes through everything and does everything automatic. But you can also tick off the different ports of your builds, like doing the platform build, isolated, analyzing it, and doing the overlay build, analyzing it, the Peta Linux stuff, and then finally the SD card. So there's different ways to get through that. Basically, I find it quite educational to go through the sub-steps instead of going through a very large build, at least for the first 1 or 2 times. So when we are building this platform, first place, that's what it looks like. We are okay with it. What it would look like when you look into the overlay build, this overlay build picks up on these kernels. So basically you're defining a kernel. When we look into this repository, just again for a short moment, you will find that there's some ESP filter, I was mentioning that before, and some kernel, some DPU overlay. These cannot go together, so you have to decide for your design finally which one to choose. But that's a makefile switch, so that's no problem. But when you do that, then the build will basically, there we are. The build will basically, come on, let me just get this out of the way for a moment. The build will then be extended to look like this. And that's, if you look at it a bit larger from what we have seen before. So when you just look at this particular item that I was mentioning before, the AI engine didn't have any kind of functional ports before. These were added due to this kind of higher level design entry from the make level of the overlay. So the overlay comes in and says like, I need so and so many inputs and outputs of the AI engine, and that basically then finally resolves into this complete build. You will still find the blocks that we were talking about before, and you will also find an additional kernel for pre-processing or post-processing of the images as they're coming in. So when you have any kind of processing that happens on the AI engine, these guys would expect a certain granularity of or a certain size, of course, of images, and you will always have to do some pre-processing. So that's basically what we have in this complete design. But you see the difference from the original plain platform design that basically has no functionality in a sense, that it doesn't use the AI engines and everything like that. But then we're going into this extended design, and what has been added from this overlay process is these additional steps. So that's just a course overview. If you really want to build these kind of things, then you will have to take care that you understand these tool flows and all of that kind of things for your own. But that's basically what we wanted to see. So what does it all help, and how do we actually go about it? It's really all about thinking from your application perspective. So if you are doing these base platforms are not your core mission statement. So you will always have to kind of get things done on top. And in the most extreme scenario, you would have an application designer that does not care about the underlying hardware in a way and tries just to map out its particular issue, a particular problem out into the hardware. And that's what we see in here. That's basically, as I said, like before, there may be some features that do AI, and that's really then the DPU, for example, in a hardware that needs to be used to accelerate computation of neural networks. So all the operators get mapped out to the DPU, and you're just faster than you would do it sequentially on the CPU. Of course, people on that level know about the model structure and about the model subtleties, but they don't know about the underlying physical implementation of the DPU. The only thing that they are concerned with is, say, like they need the constraints, like how large can images be, how large can filters be, and whatever. And that's just about it. Of course, to get this complete system running, you would need an application developer that is quite aware of these models, how to feed data into them, and how to deduce results from these elements. And underneath that, you would have to provide the data from maybe even a custom pipeline out of some interfaces or whatever. So on these designs, on these accelerated designs, you will see very different focus of contribution. And this is why this layered approach with the platforms is actually quite helpful with respect to, you could say, like a bottom-up design that gets extended and informed from the next level all time, because at some point the application defines the function that wants to be accelerated, that gets converted into a kernel and would finally then end up in a custom RTL code or in an RTL level within a big build. Behind the scenes, of course, these software-defined tools like in Vitis would still trigger, and well, basically they are rearranging the top level for these particular kernels, and they are still triggering Vivado to build the final result. So how can you actually deal with these elements from the complete stack perspective? If you want to build such a complete design, you may end up in a very high number of layers that you need to basically cover somehow in your design. And for example, when you look into the target hardware that we have in there, at some point there's this XRT layer that you need to control in order for these kernels to operate. And then on top, you can basically have some applications that make use of these kernels. All of these translation tools here are part of the tool chain. And the good thing from this TRD perspective is that for most part of the elements that you have in these boards, it's already pre-configured in these designs. So you can have a very good lookup base from these elements in this way as well. So from our perspective, we have a tool chain that basically comes in from the base platform, which we saw built in Vivado. You have some ideas of particular algorithms that you want to accelerate. You can use either the CPU to run them still, or you can use the AI engine array, or you can use HLS to convert the C code into some HDL code. And that all needs to come together on the software-defined layer. There's a linking step, as Xilinx calls it. It's the V++ linker that's used there, that is aware of these elements and is aware of the way that these should be connected, and it rearranges the top level and then finally builds the complete image. So that's what we are actually looking at in this context. The images that you're using in this case would be our SD card from the TRDs, and you can directly deploy them on the board, or you can use them in software or hardware emulation so that you would finally have a non-target related debugging capability. Of course, this all means at times you will have to tweak your results, going back into your choice of the split, what you want to do where. And this is where these kind of TRDs help you, because the base physical interfaces and all of that, what you have in there, these will not be altered. So looking at this repository again, don't forget that we were talking about the base platform before. The base platform won't alter, but what will alter is your overlays. So in this case of our design, as we have it there, the iteration will always only be considered with the overlay. Well, that said, it still means that in the end, you are having to go through full build in Vivado, because each time you rearrange your netlist in that array, of course, it will mean that it has to basically give you some insight. Okay, so from that perspective, maybe we can also look into these ideas of the kernels. As I said, like there's 3 different flavors of kernels that you could in principle have. You can incorporate RTL code as it is, as long as it adheres to the XRT level control registers that it needs. It's maybe like 8 registers or something, depending on your interfaces that you're using. You have the HLS component, which can directly, or HLS tool flow that can directly pick from your C code and map it out into HDL. That guy can be guided to create such XRT, XRT level interfaces. And the AI engine stuff is a very specific compiler that needs to create configuration data for this new IP that you have in there. And this is also aware of XRT control in a certain way. So that's what we have. When you look into HLS, just to get it mentioned in here, it's really all about keeping your effort of function closure on the C level. So you have test benches for your C code, and you basically try to get the most out of it. And then you will basically translate it into some suitable HDL code through the process of the compiler. And at each and every step that you're doing in here, you can still refer back to the test bench and use it, reuse it even for the HDL coding. So you will see any kind of difference between HDL code and C code if there turns a difference up at all, which is very typically only there for coding, well, misunderstandings, I would say. That's the way. Okay, so that then basically means you have your idea of the TRDs. Going back to this, you have this complete pipeline in between that you can govern, and you can basically plug in your mission mode codes, your own accelerators, your own mission mode elements, and you can feed it from anywhere from the input pipeline and the output pipeline, feed it into anywhere in the output pipeline. So that's really this idea. Just to mention what this whole thing looks like when you do an AI-based approach with Vitis AI, which is, as I said before, this kind of tool set that uses the DPU IP, a very broadened generic vector processing IP that is very good in doing this kind of multiply accumulate logic. It's a quite complex tool flow in a way, but it's still also very much automated. So you are coming in from this modeling level, go through the different layers of translating the model into something that the DPU can break down and digest. And you would then integrate this, or you will basically have the DPU integrated into the V++ build as well. So it's not really too much of a hassle. So what does it look like in the overall flow? So maybe when you consider data processing for some multimedia level application like this, that's what the Kriya basically provides in its standard TRD or standard design. You have the Kriya itself, which is a Zynq Ultrascale device that has a video path of different versions, even from the file system, from the USB camera, from the direct camera interfaces. You go through some pre-processing stages, that is kernels that would basically scale the images, maybe do some kind of histogram correction and these kind of things. And then you have the DPU doing some magic processing in order to identify or draw boxes around objects. And that would finally then be recombined. So that really maps out to the particular design, which means whatever camera path you use, you would go into this acceleration path that I was showing before: pre-processing, DPU, and post-processing. Post-processing in this case would mean, well, okay, it could be this kind of bounding box creation overlay on the video signal and these kind of things. So that's really what we would have on the TRD out of the box. And you don't have to go through building it, but you can go through building it. So finally, that's really what we typically should have. And I can, in the meantime, I think already switch over to, yeah, turn on the board. So if it gets a bit louder in here, I apologize already, but it's hopefully still okay for my microphone to address it. So you will see this guy booting up. That's a Kriya board now. We will see that in a second. That's just running on the other side of my desk in this case. And at some point, I'll try to basically verify that some application that I was preparing for it basically runs as well. So the idea is that what's booting right now has a bit stream that has all of these interfaces covered. I have some kind of processing pipeline in there. I think there's no DPU in there, but it may be. And we have the output pipeline in a way. So I have connected this guy to a screen. So basically something like that. And that's what I'm trying to show in this case. So it's really the same thing. If I would have used any other board, the outcome, or say the overall kind of things that I have in place, is kind of the same. We didn't talk about the Linux build, but when you look into the typical tool flow, that's just what it is. So you have some kind of hardware creation step that creates the address representation of your system. You can basically then have this information dropping into your Linux build, where you are grabbing different, well, specific libraries, of course, for the XRT and all of that thing, but that's a very common stuff. And basically these Linux projects, as we saw before, are also already provided. So when you look into the repository, as we said, we have also a Linux project in that whole thing that's by itself complete, and at parts, some come with already predefined BSPs, which means also the predetermined elements. So from that perspective, I would think that I can show, okay, that's my autofocus right now, but just let me see, that's the screen that the Kria is driving. It's not driving anything because there's no desktop management level with it. But what I can do, at least, I can try to figure out how to control it. So what I have been building in there, maybe some people see it, I have been putting in the Jupyter Lab server in there. So I could really now hook up to the board and use Python to control it. Let's just do it like this. I'm just loading the app, trying to figure out where we are coming from. So the idea is that I would have had this repository checked out, built completely, and in the end, I should be quite happy to build it through and then use it in the way that I have it. We didn't talk about, say, like the camera, the application level software of it. That's kind of a bit also involved, but for these standard TRDs, you will get some kind of demo level software already with it. Lately, you can download it also from a package management level. Oops. So you do also load app, that's what it says. Yes. And I should be able to load the smart cam thing that was on the slide. KV260 minus smart cam. And I should be able also to then start the actual cam. Let me pull that command line in. That's I'll be. So kind of started the application that's running now as a continuous camera processing thing. As I said, like I don't likely have too much stuff in there. So it's at least showing you some kind of lighter stream. I'll be put. Yeah, well, the camera. That should be at least possible to give you some kind of hint of that it's really working the way it is right now. So that's the kind of story behind the whole thing. Checking out this repository, building the complete level, and you have ready-made applications that help you with the particular effort you want to do. And then you can decide to just iterate over the overlays, and that would finally give you the results, hopefully, that you're trying to achieve. So what did we try to push today? It is all about this kind of same way of usage of this development kit so that you have these target reference designs. Typically, it's multimedia paths these days, of course, but it will basically allow you to easily operate a full stack of application on these TRDs instead of building everything up from bottom up yourself. And it will typically help a lot with getting going with your own contribution instead of just bothering about the frameworks. So that's where I wanted to end today. If you have questions, you can push them into the tool chain, into the go-to path. I can answer them right in the aftermath. Otherwise, we will be getting back to you via email. Would be nice if you consider PLC2 with respect to content that you are trying to deal with. We are always there for you. Look at our extensive course program. The topics that I was mentioning today would basically lean out into anything from embedded hardware design, embedded software design, acceleration principles, using Vitis and using even Vitis AI. So that's really a wide scale of things. I know it's kind of dense, but hopefully you got the idea. If you grab a development kit from AMD, think about the TRDs and think about the actual mission mode thing that you want to accomplish. It will speed up your work. With that, I thank you for your time, and hopefully you'll be in contact with PLC2. Thank you.